Okay, hi. I wanted to try to get a video made for you in case you can't be in class with us. For short little things on how to do stuff, I will, excuse me, try to find videos that are already made. That way I don't have to produce as many graphics or things like that because it's a little time consuming. But for more like the big concept things or the big lesson where we're at right now, I wanted to try to get one made. So I hope this makes sense to you. Anyway, so we're starting a topic right now that we refer to as functions. Some have missed some of the starting lessons, so I will make retroactively lessons on some of the things that might have been missed, but this is what we did recently and in class, and so I wanted to make sure that it made sense. So what we have here is different representations of what we refer to as a function. A function is a type of relationship between two quantities, two values, typically numerical. Really doesn't have to be. There are other relationships between variables, but we usually refer to a variable like your height, your weight, how many calories you consume in a day. We refer to these as variables. Quite possibly how much your height changes over the course of the year, especially in your childhood, could depend on your diet, how much nutrition you get. Your weight changing up or down could depend on how much you consume during a time period. Anything like that. The size of shirt you buy might have something to do with the length of your arms. In fact, it usually does. But the idea here is that two numbers in the world can have a relationship with each other, how warm or cool you feel might have to do with the temperature in the room, or how comfortable you are. The relationship between two quantities like this can change over time, or as one quantity changes, that could drive the other quantity to change. So I don't know if milk makes you grow taller, but maybe how much milk you drink, if the more milk you drink, maybe the taller you'll get. I don't know if that's true, but you've heard maybe it's suggested. Oh, so I got this recording window up. So the idea here is that a function represents a dependence of one number on another. So if I said that how tall you grew, some people think may be a function of the amount of milk you drink. Then what we're saying is that one kind of drives the other. We would refer to what we call the input variable as the independent function. That does its own thing. But the amount that you grow is the dependent variable because it's more like the output of the scenario. You pick a level of milk consumption and you get out a different number of inches grown that year. I'm just making up examples. You'll come to know that I am not good at that, so I apologize in advance. But that's the kind of relationship we're dealing with here, is that one thing depends on the other, not really necessarily the other way around. We will get to thinking about inverse relationships eventually, but right now, when we talk about a function, what we mean is something that is an outcome, is a function of something else. It depends on something else. There is an input, and then it is an output in a way. It represents a mapping of inputs into outputs. No milk, a couple inches. A little milk, maybe more inches. A lot of milk, no real change. Same as a little milk. So the functions can basically describe how different inputs can map out into different outputs. It's a pretty important concept in all the quantitative sciences and the applications of those. But so I guess that's the gist of it. We have different ways of representing the way there could be a relationship between inputs and outputs. These notions, when we refer to a function, they kind of capture natural relationships, and a good way to think about it is things that vary with time. Like I know in physics classes, you might be used to seeing a coordinate system like you see on the right. You might have seen those before, where you had an x, which was a distance east and west, and then a y that represented a distance north and south from some reference point that we call the origin. Well, in some disciplines, like in physics, one axis might represent an amount of time that's passed, and the other axis represents what a certain quantity is doing right now. So let's say how fast you're moving. Maybe you start off really slow, so when time is back here at the start, your speed is low. But as you advance in time, your speed rises, and you might see a function that climbs a little bit. Maybe a linear function, maybe a line, rising with a positive slope. In that case, you get this notion of, well, that line isn't a mark on my page. It's representing the way something, an object is moving in time. The line is represents its motion. The object is not the line. The line at any one point, as you go along in time, tells you where the object is based on the point. So with that kind of a thinking about things that vary, as the clock ticks, where's the car, something like that, then you get some notions that the curves need to be able to convey natural motion. So for instance, if a car is at one part of its journey, and then later the car is at another part of its journey, it actually had to travel all that space in between, because that's what cars do. They don't just blink out of existence and blink back into existence somewhere else. The curve needs to have certain properties that say cars move from here to there, and they can't exist at more than one place at one time. So after I explain these different representations, I'd like to show you the difference between things that we consider functions and things that are still relationships, just not functions when we use that word function. So let me now explain what I've got on the screen here. These are different representations of the same relationships between sets of numbers. The numbers probably most clear here on the left as a mapping diagram. Here we use these bubbles to represent different sets of numbers. The domain, you can think of that as all the input values that could be inputted. You know, all the different levels of milk drinking, how many cups in a day, or something like that. And the range could represent, I wasn't thinking of that when I made this example, but the milk. So that probably won't make sense as we look at it. But the numbers on the right could represent a set of numbers which represent the outputs, or a number of inches grown in a year. And the function, the relationship between those things for milk drinking, or maybe even coffee drinking, maybe there's a different association there. The domain would be all the inputs that you could have, maybe the number of cups, and the mapping is represented with the arrows. I just sort of did random arrows, and here you see that if I input 1, this will output a 9. If I input a 2, this will output a 3. Likewise, if I input a 6, it will output a 3. If I input the 5, I'll get out a 2. And if I input a 7, I'll get out an 11. So that's what we mean by domain and range of a function. And what we mean that a function is. It's an association between inputs and outputs. It describes that relationship. It actually quantifies that relationship. And there are different functions that map one set of numbers to another set of numbers. Maybe they're the same sets that they map, but they map them in a different way. Okay, so domain inputs, range outputs. That's kind of the terminology. Well, there's more than one way. We didn't have to use arrows. We could have used a table. So inputs on the left, outputs on the right. And there you see an example of the table. It is the exact same relationship that I have represented here with the mapping diagram. Very similar to the table is a table written in another way. We call these ordered pairs because it's always x then y. It's always the input and the output. I'm using this like set notation. That's a curly bracket, and that's containing a set of points which are the same as the rows on the table. So that's another representation of the same mapping of inputs to outputs. And finally, there is the graph and plot, which is pretty much the same as the ordered pair. The difference being is that you can see it kind of more visually, where 1 is the horizontal address of each dot. I'm sorry, the inputs. The inputs would be the horizontal address. On a 2D grid, you need 2 numbers to define where it's at. There's the horizontal axis. How far parallel to the x-axis must you walk? And then how far parallel to the y-axis must you walk to get to any place? You need those 2 numbers. We can show the relationship between inputs and outputs as a graph or as a plot where the input is the horizontal axis and the or coordinate, and the output number is the vertical axis. And like I said, I chose kind of random numbers, so it doesn't look like there's any meaningful thing going on here. Okay, so I hope that made some sense to you. This is just a way that we represent that kind of a relationship between quantities, and that's the language that we're using for this. Then, so to make sure that you get it, well, I do have a little bit more to say about rules about what a function can be and can't be. So I'm showing you now, if I scroll down here, I just copied and pasted that, and I just changed it a little bit. This one I changed kind of uniquely, but the rest of these I made the same change in every case. So on the left with the mapping diagram, before we had a function, and now we don't. So I'm showing you the thing that the first questions that you might see will ask you to notice so that you know that that's not a function. And I've highlighted that in red. Before with the mapping function, it was okay that two different outputs, that two different inputs gave the same output. So again, if that was like milk in inches, well, if I drank 2 cups a week versus 6, I still grow 3 inches. Okay, that's fine. That's possible. There's nothing illogical about that. But this is not okay. If I drink 1 cup of milk, I'll grow both 3 inches this year and I'll grow 9 inches this year. You can't do both of those at once. So having more than one arrow coming into a number on the output side is okay. 2 things can do the same thing. That's fine. But one thing can't do 2 things, if that makes sense. It can't have 2 effects at once. Either it's here or it's there. So that one's an illogical kind of thing there. In the way that we like to use functions and the limitations that we put on functions and what we mean by that when we use that word. Okay, I made the same error, well, type of error, in the other examples. So instead of having 5 mapped to 2 and 6 mapped to 3, I made the 6 a 5. So now 5 maps to 2 and 5 maps to 3. So if the questions you get say, is this a function? You would say, yeah, that's a function. Because every element in the domain, all the inputs, have one unique output. Whereas in this case, 5 has 2 different outputs. So that's not a function in this changed version. In the ordered pair, I did the same thing. If you see a 5 as the x value repeated and 2 different y values, again, 1 input, 2 outputs. 1 cause, 2 different effects, so that's you would, if you see that, the 3s are okay because they're the outputs. You can have that, but the inputs can't be have 2 different outputs. So look for that in those types of questions. And as a graph, it's whenever the same horizontal address has multiple vertical addresses. So, well, which one is it? Like at, however, what is that? Maybe 7 seconds in. Is my car here or is it there? How can it be at both? if these represent where my car is against the clock, against time. So that's the problem with those. So that's the examples that I have for you to see, to tell when you have a function or not. To explain a tool that we have in the case of a graph of a function, we have what we call the vertical line test. So I've got this line here, and I've got different functions, and I've shown that this one is as far as I can see, it is a function. And I should probably have arrows at the end to show that they keep going. So I'm going to take my vertical line, and as I scan over this, I'll notice that it only crosses the function at one place at any time or at any location I put this. And because I never intersect it more than one time, it passes the vertical line test. So that is a function. That is 1-to-1. Every input gets its own output. no input has 2, like up here. This one you'll see right away. The function doesn't exist over here, but when I come over here, actually this isn't a function because it does not pass the vertical line test. Okay. Now, that doesn't mean it's a bad shape. Everybody loves a circle, right? But look at that. It doesn't pass. It has 2 intersections with the vertical line test. And usually we like to read left to right, so I'll do that. This one, align, pretty simply and obviously passes the vertical line test. So that's how you can, you don't have to worry about a horizontal line test. There's no such thing for functions. You don't have to pass that, and you can still be a function. This one does pass it, but it's not a function anyway. So I hope that helps. I wanted to make sure that you were aware of the lesson topics and how to answer some of the first questions that you'll see. So let me know if you need anything or have any questions, and I will try to answer them. Have a great day.